In this segment, we'll add two new tables to keep track of discount offerings in Bakery 2. And this will involve N to M relationships, and we'll introduce junction tables to represent such relationships. A discount offering is a percent discount on a product's price, effective from some start date to some end date, and it's applicable to one or more products. We'll add a discount table to keep track of these, and here's a quick select star on that table. And you can see that in the database we have 4 discounts, each with a primary key ID, and then a starting date and an ending date and a percentage off. Now, each discount may apply to multiple products, and each product may participate in multiple discounts. So the big question then is, how would we represent this in the database? First question, would it work just to add a foreign key to product, say product.discountID, that links product to discount in order to show what discount a product participates in? That would allow any number of products to link to a single discount. Or perhaps we could add a discount.productID field to discount, another field to the 4 that are listed here. That would mean that any number of discounts could apply to the same product. Would either of these solve the problem of having many discounts and many products apply to one another? And if you think about it, the answer is no, it really wouldn't. Neither of those will do it. Adding a foreign key discount ID to product allows many products to participate in the same discount, but it doesn't allow one product to participate in many discounts, since each product could only have one foreign key reference to one discount. And the reverse is similar. We could add a foreign key product ID to the discount table that we're looking at here, and that lets one product be pointed to by many discounts, but it does not allow any one discount to refer to more than one product. You'd think that having both foreign keys might solve the problem, but this still means that each product can only link to one discount and each discount to one product. And if you don't see the problem with this, then consider how you show every product linked with every discount. That could conceivably happen. And could we do that using just 2 foreign keys, from product to discount and then another from discount to product? If there were, say, 100 products and 50 discounts, then tables product and discount would have only 150 foreign key values to point back and forth between them, but there could be as many as 5,000 discount product connections. This is really the core problem. If there are n discounts and m products, then there are n times m possible connections between discounts and products, which is more than can be represented by a foreign key in one table or the other, or even both. This is an example of an n by m relationship, or more commonly just an nm relationship. So how do we represent this using foreign keys? Interestingly, by a table. Let's do a select star now on table discount x product, which is the other new table in the Bakery 2 database that's been added. As you can see, it has only 2 columns, discount ID and product ID. Each row of the table serves the sole purpose of indicating that a given discount applies to a given product, and the table has as many rows as there are discount product connections. Such a junction table, also sometimes called an association table or a join table, and half a dozen other names as it turns out. This is the standard SQL way, a junction table, to represent an n-m relationship. Now, some designers do prefer more meaningful names for junction tables, like product has discount or discount includes product. The argument for the neutral name, discount x product, is that it's highly predictable and easily remembered name for a junction table between discount and product, and it doesn't favor either side of what is a bilateral relationship. In our design, we'll even put the 2 connected table names in alphabetic order in the junction table name. So it's discount x product, not product x discount, and that makes the name completely predictable. From the output of our select here, we can see that the 4 discounts in bakery each apply to 2 to 4 products apiece, for a total of 11 discount product connections. And even if every one of our 4 discounts had applied to every one of our 40 products, we could still represent that with a total of 4 times 40, or 160 rows in discount X product. Now, question 2, just to be sure you see how it works. Do any products fall under several discounts? The answer is sure, yeah. Product 46-11, for instance, is affected by discount 1 and also by discount 4 and discount 5. And 90-ALM-1 here is affected by discounts 5 and 6. Okay, question 3. Augment the ERD for bakery to show the new discount and discount X product tables, or entities if you want to use the technical term, along with 2 new relationships that they introduce. So just hand draw what you think would be the augmenting or the addition to the ERD for bakery 2. And what you should come up with then is something like this. Two new tables, discount X product and discount, and there are 1 to N relationships from product to discount X product and from discount to discount X product. Discount X product is the N side in each relationship. One product may correspond to many discount product combination rows, and so may one discount. And again, a side note here, a more abstract ERD, like we discussed in an earlier lecture briefly, might replace the entire discount X product table with a diamond that indicates an N-to-M relationship between discount and product. From the abstract view, the table discount X product is just an implementation detail. But our practical ERD is going to show the junction table explicitly, since we have to deal with it in queries and other operations. So, speaking of doing so, question 4. Write and test a query listing which products are covered by discount 1. Just list the product IDs. You should get 4 rows. And write a second query listing what discounts apply to product 46-11, giving the discount IDs. There you should get 3 rows. And use a join only if needed, and use distinct only if needed. So the answer is, these are pretty simple queries actually. You really only need to address discount X product. That'll suffice if all you want are the IDs. So here's the one for discount 1, and the one for product 4611 is similar. Thus, and since discount X product will have at most 1 row for any product discount combination, then distinct would be superfluous in this case. And question 5. So now list all receipt IDs without repetition for which at least one purchased item in the receipt was discounted by over 25%. It's tempting to think you'll need to join with receipt and product to do this, but if you think about it, you should need just 3 tables and 2 joins. You should get 58 rows. And the solution you might have come up with is this. We're going to need to join with product. We only need to join with product if we wanted product information beyond the product ID. And the same is true for receipt. So we only need line item, discount X product, and discount for this query. And you can see we're joining through those 3 tables with the appropriate foreign key links. And then we're also checking that the percentage off for the discount linked be greater than 25. And we do need a distinct, since receipt ID might be repeated. The same receipt might show in multiple high-end discounts, or more than 25% discounts. And there's the 58 rows. Okay, now question 7. Try getting all receipts that list at least 1 item on discount, giving the receipt ID in sorted order, and listing each receipt ID at most once. For this, you should need to join 4 tables. And interestingly, product again is not among them. You should get 18 results. If you get more results, especially 58 of them, look closely at every column of discount. You need to use all but one of discount's columns. So I came up with this. Here we're going to join across receipt, line item, discount X product, and discount. And we'll have the expected 3 clauses to connect foreign key and primary key pairs. And we can skip over product and go straight to discount X product, since the latter has the product ID foreign key column. And we do need to check that the receipt's purchase date falls within the start date and end date of the discount in question. Missing that test, by the way, is how you might have gotten 58 results. And you can see we did use almost every single column of discount then to do this. Okay, and then finally, question 8. Extend that query that we just wrote to list all customers who have purchased items on discount, giving at least their last name and first name in the usual last name, first name sorting order. List each customer at most once. You should need to join 5 tables to do this, and you should get 14 results, not 18 as in the prior query, because some of those receipts are the same customers. So there's what I came up with. And it's the same query we had before. I just added in customer among the tables that are being joined and the appropriate foreign key, primary key link to do that. And then did also add customer.id and distinct, as we have in the past with queries, to ensure that we had unique customers but would have distinct ones if they had the same last and first name. And then we do have the order by at the end for last name and first name.